you all know Simon. He's been visiting us several times in Germany. He's currently affiliated with a lot of groups, INRIA, CWI, and he's also working sometimes from Cairns. So yeah, he's going to talk about quantum speedup for graph Sparsification, cut approximation, and Laplacian solving, which is his recent paper with Ronald.
Okay, thank you. So I don't have to push anything, right? This is
it's already.
Okay, perfect. Yeah, so like Shantana kindly introduced, I'll be talking about joint work with Ronald de Wolf, who's at CWI and QSoft and Amsterdam, which is University of Amsterdam, which is all within a radius of a couple hundred meters. And we worked on quantum algorithms for a problem called graph sparsification, which is interesting because that led to quantum speedup for a number of other problems like cut approximation and Laplacian solving. So there's going to be some graph theoretic and like classical theoretic computer science in there. So please feel very free to interrupt at any point or ask questions. Like, I'd be very happy to know where everybody is. So first I'll introduce this problem called graph sparsification. The problem of graph sparsification is kind of a fundamental problem. You are given a undirected and weighted graph. This graph has n nodes and m edges. It is a simple graph in the sense that there's no multiple edges. Like between any pair of nodes, there's a potential edge with a certain weight. So it means that this graph can have as much as n squared edges. And kind of seems that, okay, like in order to describe this graph, that's what you need, right? You need to describe these n squared edges. It turns out that for a lot of problems, that's not quite the case. You can actually create a much sparser graph, which still captures most of the important information about the graph. So we'll assume adjacency list access. What does that mean? It means that we know the node list. You can just think about it as the integers from 1 to n. And from every node, we can ask, like, what are my neighbors, pretty much. So this is like a sparse access model to the graph. Now, graph sparsification is about the following thing. What we want to do is we want to reduce this number of edges. So recall we have a graph on n nodes, which is going to be constant. But we want to reduce the number of edges, right? So we can have as much as n squared edges in an arbitrary graph. And we want to bring this down and basically compress this graph to a more sparse graph. So what we want to do is we want to reduce the number of edges while preserving certain quantities, of course, because you could just throw away all edges, but then we lose everything that we kind of had of information. Now, what does it mean? Preserve certain quantities. It can have a lot of meanings. In this particular talk, it'll mean something which is related to what we call the graph Laplacian. The graph Laplacian is a matrix associated to the graph, and this matrix actually captures most of the information about the graph. So how do you define it? The graph Laplacian, Lg, is defined as d minus a, where d is the degree matrix. So basically for every node, you look at the total edge weight of edges connected to this node. So if the graph is unweighted, this would just be the degree of the node. This is a diagonal matrix just containing these things, and A is the weighted adjacency matrix, right? So an element ij just contains the weight between node I and node j. And this is what we call a linear algebraic characterization of the graph G. It's very useful for a lot of purposes. Like what you can see is that you can associate things called quadratic forms to this Laplacian, which are just scalars that you extract from this Laplacian. All right, so you can define a quadratic form x transpose Lgx, where x is just some arbitrary complex valued vector. And you can do the same thing with L plus, and L plus will be the pseudo inverse of the Laplacian. So the Laplacian is full rank up to one trivial kernel vector, which is just the all ones. But okay, it's not very important. So typically you can just think about that being the inverse. And what's interesting is that these quadratic forms associated to this Laplacian, they describe cut values. So if you take x to be an indicator on a certain subset, then this describes the value of the cut basically described by this subset. So if you cut all edges going out of that subset, you sum these weights, That's what's described by this quadratic form. You can also express eigenvalues, effective resistances, hitting times, and so on, all using these kind of quadratic forms of Laplacian. And that?
Explain the cut value again, kind of.
Okay, the cut value is basically like you have a certain graph, you have a subset S. Oh, okay. So let's say you have a certain graph G, you have a node subset S, and you can define the value of S, or basically the value of the cut S as complement, as the number of edges that you have to cut. I mean, the sort of weighted sum of the edges that you have to cut. So you sum over all I in S, J in the complement of S, and you just sum all the weights. Right, so for an unweighted graph, this is just the number of edges between S and its complement. Right, so that's why you call it the cut value. Like if you want to cut the graph in two parts, one being S, the other being the complement, and the number of edges that you have to cut is basically the cut value. And this is captured very nicely by this quadratic form in the Laplacian. And so it turns out that, okay, these quadratic forms, they really capture a lot of information about the graph, and this motivates the definition of spectral sparsification, which is a certain form of graph sparsification, where we, again, want to sparsify the graph, so we want to go from this dense graph to the sparser graph, and now the goal is to approximately preserve all quadratic forms. So that means H has a Laplacian associated to it, and we want that the quadratic forms in the Laplacian of H, so this term here, epsilon approximates, so that's an epsilon multiplicative error, epsilon approximates the quadratic forms in the original G, so this should be like a superscript. So basically that means that if you're interested in quadratic forms of the Laplacian, then I can essentially just send you the sparsified graph, and then you can approximate all quadratic forms that you were originally interested in. And you want that this is the case for every x, right? So we don't want that this holds with high probability. We want that this holds for every vector x over the node set of H. An equivalent formulation you can show that is that basically quadratic forms in the inverse or pseudo-inverse are also preserved, or you can use this sort of PSD ordering, which just expresses the same condition pretty much. Okay? So this is the notion that we're interested in. And there's a very interesting theorem related to spectral sparsification, which by Spielmann and Tang, who are actually the guys that introduced the concept of spectral sparsification. And what they did is they showed that one thing which is a very non-trivial statement is that every graph, so any graph you can come up with arbitrary weights, has a epsilon spectral sparsifier. So that means, like I just said, like a graph H that epsilon approximates all quadratic forms with a number of edges, which is O tilde n over epsilon squared. So that is a very sparse graph, right? So let's say that we're interested in preserving all quadratic forms up to a constant error. The epsilon would be constant, and basically we just have O tilde n edges in the new graph. They later on improved this actually to get rid of the tilde. You can just like, so this is a very, very remarkable result, right? Like for instance, if you think about this original graph, you go to this graph, I can actually send you a graph which is very sparse, and it approximates all, like say, all cut values of the original graph, but then again, like a lot more, like also all effect resistances, all the entire spectral structure basically is captured by a much sparser graph. And so this very non-trivial statement that it's possible. What makes it even more non-trivial is that they show that you can actually find the sparsifier efficiently. You can find it in time O tilde m, where m is the number of edges, right? So this can be as much as n squared. And it's very interesting because what you can now do is you can actually simplify a lot of problems, right? So let's say that you're interested in cut approximation algorithms, right? So we just define what a cut is, and there's a lot of problems associated to graphs which ask, say, what is the min cut or max cut or min ST cut that separates nodes S and T and so on. So for all these problems, you can basically do the following. That is, if you're satisfied with an epsilon approximate solution, you first sparsify your graph, which takes O tilde m time by the Spielmann-Tang algorithm, and then you solve the problem in the much sparser graph. And typically these problems really get more difficult when the graph is denser, and so you're very happy with that you can basically solve them on the sparsified graph. And this gives you basically utility M approximation algorithms for a lot of problems like max cut, min ST cut, sparse cut, and so on, which all kind of use this notion. Right? So this is a much older paper which used a sort of more like rougher form of graph sparsification, but it used the same idea. Then there's even more. The reason why Spielmann and Tang were interested in spectral sparsification rather than this rougher form that I just mentioned is because if H is an absolute spectral sparsifier of G, then you get that the Laplacian system, so this is like a linear system in the graph Laplacian, of the sparsifier actually approximates the original linear system. So that means that you can actually, if you want to solve this original linear system in the graph Laplacian, which is something that you very often have to do in graph theory, then you can actually solve this in a much sparser H graph. And this led them to prove that for any graph with M edges, you can basically solve this original Laplacian system in time with tilde M. And here again, the idea is that you just sparsify G to get a much sparser graph, which you can work with more easily, and then solve the system in this sparsified graph, which approximates the solution of the original graph. I mean, their algorithm goes a bit further than that, but that's kind of the main idea. That's why they were interested in this problem. This on its turn led to a lot of approximation algorithms. This is what we call near linear. So the initial graph has M edges, so its description size is M. And so you get all these approximation algorithms which are near linear in the input size for things like electrical flows, spectral clustering, random walk properties, learning from data on graphs, and so on and so on. Okay, so kind of, I think, nicely illustrates that this is really an interesting concept, and that's exactly why we were looking at it. Okay, so what we wanted to do is we wanted to ask the question, like, can we find quantum algorithms which basically sparsify graphs? And we showed that indeed this is possible. Namely, what we showed is that we proposed a quantum algorithm that finds an epsilon spectral sparsifier in time O tilde square root mn over epsilon. Right? So recall that originally you had complexity which is O tilde m. I have to kind of maybe make a small side remark regarding this bound. So classically, what you get is you get basically O tilde m, but like implicitly there's like this n over epsilon squared term here, because this is the size of the sparsifier H, right? And so clearly your algorithm is lower bounded by the description size of the output, but you never mention this thing because if this would be larger than m, then you would never sparsify your graph, because the sparsified graph will have that many edges, and otherwise you just keep the original graph. And so quantumly, so why I'm saying this is because quantumly what we get pretty much the same thing, square root mn over epsilon plus n over epsilon squared. What I want to argue is that this unconditionally improves on this thing because, again, by the same thing, sparsification is only relevant if m is larger than n over epsilon squared, and this is basically satisfied if and only if epsilon is large enough. Basically, epsilon should be larger than n over m for sparsification to be useful. And so if you plug this thing in here, then you get m, basically. So what you get is that for the useful regime, this always improves on the classical algorithm. Okay?
So why is the epsilon squared dependence?
In here?
Yeah.
So this is basically what follows from the Spielmann-Tang algorithm. So they showed there is a spectral sparsifier which has n over epsilon squared edges, but you can actually show that this is optimal. You can actually show that, and this is you can see it as a sort of result of they use matrix concentration inequalities, and they use sort of Chernoff bound, and there you get some epsilon squared dependency, and it turns out you cannot get rid of that.
So for the quantum result also you got is there a matching lower bound?
Yes. So that would be my second bullet. So the first one was that we find this quantum algorithm which gives the absolute spectral sparsifier in this complexity. And the second bullet is exactly what you're asking about, is we prove it is optimal, right? Just like in a classical case, you can prove that you cannot improve on that. Here we get the same thing. So this kind of, again, justifies why this is like the correct dependency. And so finally, we discuss a quantum speedup for a number of problems that kind of follows from our quantum algorithm for graph sparsification. Okay? So I'll first talk a bit about this quantum algorithm that we have. To do so, I'll first discuss some classical sparsification algorithms and kind of give you the gist or the idea of how these algorithms work. So what they do is, recall that you have this set of n squared, or like m edges. So classical, you associate a certain probability to every edge, where this is like, you got to think about it as an independent random variable for every edge. So these PEs, they don't sum to 1. Like you can basically associate probability 1 to every edge, which would not be very useful, but because in step 2, what you'll do is you'll keep every edge with probability PE, basically. So if you choose all PEs very large, then you're going to keep pretty much all edges. So this is not going to be a very useful thing, but you kind of know that you like preserve the structure and like quantities of the original graph. And so this kind of the game is to bring down these edge probabilities so that you get a sparser graph, but at the same time you want to keep them high enough so that you preserve certain quantities of the graph. So what you do is you keep every edge with probability PE, and if you keep it, you rescale its weight by 1 over PE. So why is that? That's basically to ensure that the expected weight of every edge remains the same. Right? So the expected weight of a certain edge in H just equals its weight in G. And you can say the same thing if you take the element-wise expectation over the Laplacian. And again, so note that the number of edges, the expected number of edges equals the sum of these PEs over all edges. And so this can be much larger than 1, right? So they don't sum to 1. So how do you basically go about this first step? So how do you associate the probabilities to the edges? You notice that important edges should get a higher PE, right? So let's look at this graph. So we call it a dumbbell graph, and like I said, the sparsifier should preserve all cuts. So we can think about this cut, for instance. Like let's say that this would be S, and this would be the complement of S. Then we know that, let's say that this graph was unweighted, the cut value is 1, right? Now if we take a sparsifier, that would be a subgraph of this graph. Then we know that this edge should still be present, because if it would not be present, then we can again look at the same cut, and we would see that we would get value 0 instead of 1. And we need a multiplicative error, and so we need this edge to be there. So that's why this is a very important edge. You cannot make the same argument about any of these other edges. Like for any individual edge, you cannot make a statement claiming that it's like that you cannot miss it. Like these are all redundant in some sense. And so the game is here that you can associate a larger probability to this central edge and a smaller probability to all the other edges. But of course, I mean, in this example, this would be very clear, but in a more general graphic, how do we quantify the importance of edges? Like, how do we find the edges which are important and detect the one, or like mark the ones that are not important? It turns out that a certain quantity associated to an edge, which is called the effective resistance, is the correct quantity. So what the effective resistance is, imagine this graph as being an electric network. What does it mean? It means that every edge is replaced by a resistor. Say if it's a unit weight edge, every resistor would just have value 1. And now you can ask about what is the effective resistance between two nodes. And so recall from high school that if you have two nodes and there's a lot of parallel paths between these two nodes, then the effective resistance will be low, whereas otherwise it will be high. And so you see that if you take, say, this edge, then you get like just so many parallel paths, which could kind of substitute for this single edge. Whereas here you don't have that. There's just a single path, and so this guy will have very large effective resistance, whereas all these edges have very small effective resistance. In fact, you can show that the red edge has a constant effective resistance, whereas the other ones have an effective resistance, which scales as 1 over n. Okay, so this seems to be like the right measure, and indeed, Spielmann and Srivastava showed that choosing these PEs proportional to these REs, which are the effective resistances, and then there's some overhead, yields an epsilon spectral sparsifier with the expected number of edges. with high probability. But then, of course, it brings us to the question, like, how can we calculate or sample according to these REs? Because, like I said, mathematically this is the right notion, but you cannot just read from the graph what the effective resistance is between edges. Even more, it's not easy to calculate these things, right? Because you have to kind of take into account the number of parallel paths and so on, so it's a very non-trivial thing. So there's an alternative route to go about creating a sparsifier, which is somewhat more combinatorial. What you just do is you find and keep the n over epsilon squared most important edges. So that means that you just have to kind of search for some important edges and then like uniformly degrade the other edges. So what you can do is, let's say that you do that, you look for these n over epsilon squared most important edges, then you can just discard all the other edges with probability 1/2 individually, right? So you kind of, okay, so again, you identify these most important edges. These you give a p equal to 1, so you keep these for certain. The other ones you give a p equal to 1/2. This is an alternative route, but of course, I mean, again, how would you find these most important edges? And now what you can do is you can use a somewhat more like combinatorial notion. Like one approach would be to grow a spanning tree, because like in this graph, you can see that if there, or actually in any graph, if there's one edge which is connectivity critical in the sense that if you would remove it, then the graph would no longer be connected, then any spanning tree, so for clarity, a spanning tree is a subgraph with n-1 edges that connects all nodes. So it's like a tree graph which has the same connectivity as a graph. So in this graph, you see that any spanning tree must necessarily contain this edge. And for any graph, you can show that all kind of connectivity critical edges are identified by spanning trees. So that would be seem like a good idea. We would do the following thing. We have this graph, we grow the spanning tree. All the edge of the spanning tree we keep. Yeah?
Would you repeat the spanning tree part, because you said the definition and then you have to...
Okay, so what a spanning tree is that your question?
Yeah, and the argument after.
Okay, so a spanning tree is a subgraph which is a tree. So it has at most n-1 edges, but if the graph is connected, then it'll have n-1 edges. Basically, that connects all nodes that were originally connected. So that means that this node and this node, they're connected in the original graph, right? There's a path between them. And so the tree is a subgraph, and you remove all the remaining edges, you take that subgraph, and then these still have to be connected. So that means that any spanning tree must necessarily contain this edge. And you can prove that this should actually be the case for any, what you call connectivity critical edge, like any edge that's important. Like if you drop it, you decrease the connectivity. Like, I mean, this one should be present in the spanning tree. And so the algorithm looks like that. Then you grow the spanning tree, you keep all these, and then you basically keep like a random half of the remaining edges. We do this thing. And it seems to work quite nicely, except that it doesn't. Namely, you can think about this graph, where you have like a lot of kind of parallel cycles, something like that, and then you have a single edge in between. And so what you see here is that this is a nice example where S and T are connected in both graphs, but in this graph, their effective resistance would be very small, whereas in this graph, it would be very large. And since sparsifiers also have to preserve effective resistance of the graph, any sparsifier should also contain this edge. You can basically prove that. And now what you can notice is that a spanning tree should not contain this edge. A spanning tree is not kind of destined to identify this edge. Namely, a spanning tree can just always go around the graph. So you might lose that edge if you use spanning trees. So there's a more refined notion, which is called a graph spanner. This is again a subgraph of G, which is very sparse. But now all distances are stretched by a small factor. Now, what does that mean? Like you take two nodes S and T. They have a shortest path in the original graph. Now you want that in the spanner, which is a subgraph, the distance is not stretched by too long. So since you're taking a subgraph, the distance will increase because you're only removing edges, but you want that it doesn't increase by too much. So in this case, you should definitely keep this edge because their distance would be 1, and removing this edge would make it like something scale like n or something like that. So this captures connectivity and distance, and this will turn out to be the right notion. Now, luckily, every graph contains a span, so this thing exists, and you can also find it efficiently. And so now we get to the following algorithm, where again we construct a number of disjoint spanners, which will identify the important edges, and we just discard like half of the remaining edges. And this is an algorithm which was recently proposed by Kutz and Su, and they show that this algorithm works in the sense that it gives an epsilon spectral sparsifier with approximately half the number of edges of the original graph. So you can just do that a log number of times, and that will give you an epsilon spectral sparsifier in the end. Okay? So any questions about this classical algorithm so far? No? Okay. So we'll go to the quantum sparsification algorithm, which consists of two routines. One is a quantum spanner construction, right? So again, the spanner construction serves for identifying the important edges. It will show that we can do faster quantumly. And the second thing, which is kind of interesting, is we need something which is called k-independent advice.
So most of the things, the examples that you were giving were for unweighted graphs, so they naturally extend to weighted graphs.
Exactly, yeah. So this was the iterative sparsification algorithm that I just showed, right? You construct a number of spanners which identify the important edges, and then you like discard half of the remaining edges. So the spanner construction is the main cost, which has cost O tilde m, and so we want to improve that. So what we show is that there's a quantum algorithm that constructs a spanner in time O tilde square root mn. So that'll typically be the kind of improvement that we find. We go from m to square root mn, something like that. I'm gonna, in the interest of time, maybe not go through the too much detail of this algorithm. Basically, it's there's a classical algorithm called the Thorup-Zwick algorithm, where you have a graph like this, and you kind of take random subsets, but nested subsets, right? So you start from this entire set of nodes, and you take a random subset of that with half the nodes, and then you take a random subset of that, and so on. And this kind of gives you like a layering of the nodes, like. The red nodes, would be approximately half of the nodes, and then you take half of them, you add another circle, and you get that the nodes in the last layer would be the very important ones, which are kind of spread out, and then you will layer below that. These would be like, you would have more nodes, even better spread out. And the idea is kind of that you want to now sparsify the graph, or like, remove edges, while keeping approximately the distances. And the idea is basically that you want to kind of find efficient routings of nodes along these. So this like would be a very important hub, right? These kind of spread out final nodes, and you'll kind of find efficient hubs between all nodes. And you can ensure that basically for every node looking at a local cluster, which you probably define, and then you want to route this local cluster, and for that you grow a shortest path tree. So what does that mean? It just means you have a node V and you have a cluster C of V, which is just a set of nodes, and you want to grow a tree which contains all the shortest paths from V to every individual node. So it's like a tree with V being the root, but every path to a node in the tree should be the shortest path in the original graph, right? So it's kind of a routing, right? You can kind of bound complexity and so on. And in the end, you get an algorithm which has complexity O tilde m. So this is the classical Thorup-Zwick algorithm. We improved this algorithm by essentially building on existing work, which is work by Duur, Heiligman, Heuer, and Mala from 2004, where they showed that this one important routine, which is the routine of growing shortest path tree, can be improved from m to square root mn. So we build on that, and we substitute that in the original algorithm, and we're kind of lucky that there's some maths that we have to take into account, but it's all kind of straightforward. So what we get in the end is so the gist is really that we use this Duur, Heiligman, Heuer, Mala algorithm to speed up this one costly routine in the Thorup-Zwick algorithm, and we find the square root mn algorithm for constructing spanners. All right. So now we can propose the following algorithm. We use a quantum algorithm to construct these spanners. So we just construct a couple of spanners which identify the important edges, and then we discard half of the remaining edges. And that's good because that works. Namely, we get a epsilon spectral sparsifier with approximately half the number of edges of the original graph. But what's not so good is that it's not at all clear. Okay, so like I said before, we're not done there, right? Because we just have the number of edges, but we want to go to approximately n edges. And so we have to take a logarithmic number of steps, like iterations of this thing. But the problem is, originally, right, we're given adjacency list access to this graph, which we cannot fully describe even because we want to do things in time which is smaller than m. So we're assuming query access to this graph. And now we construct these spanners, so we get a set of important edges, which is just a set of approximately n over epsilon squared edges. So these we can explicitly describe, that's fine. But now we want to like randomly throw away half of the edges of this list. But it's not at all clear how to do that, because we have query access to a list. Now we want to throw away half of this list, but in a random way, which now gives you like an intermediate graph with approximately m over 2 edges, and then you want to reiterate this routine on this intermediate graph. But the thing is, we cannot write down this intermediate graph because it's still much too large, right? So it's m over 2 edges. So how do we keep track of this intermediate graph? Right, because so this is a picture of the algorithm pretty much. Like you start with an adjacency list that you have access to, and you have sparsified the graph. But this one you cannot even write down fully, right? But then you will continue and end up with a very sparse graph that you can explicitly describe. But you're kind of working with these intermediate graphs that you cannot fully describe. So this was a problem that we had to work with, and we came up with the following approach. An adjacency list query looks like this, right? We have a node I and an index k, which asks for the kth neighbor of the ith node, which would be L, let's say. So this is oracle access to the graph, OG. And what our idea was to, for the moment, assume, so you have to allow me to assume this, that we have a random advice string, right? So it would be a random advice string of m bits, which basically signifies or marks whether a certain edge is present or not. So that means that we can query for an edge to the original graph, and then check in this random advice string whether the corresponding bit is 0 or 1, which will tell us whether this edge is present or not. So we get this sort of following new thing, which is adjacency list access plus an advice string. And that basically looks like that, right? So we ask for the kth neighbor of I, and so we get which is this neighbor, and whether it's still present or not, the corresponding edge. Okay. Right, so now we can imagine doing the same thing, and it turns out that we can actually, this basically suffices. So if we have actually this random advice string, then in our spanner algorithm, we can kind of set the corresponding weight of the edge that we don't want to use, which is supposed to be discarded, to 0, and so the spanner will avoid these, and this all works out pretty well. So we get an implicit description of the intermediate graphs, which is all we need for our algorithm to run, basically. Okay, so this just says that we can grow spanners in the intermediate graphs using this sort of augmented access to the graph. And this brings us to this algorithm. But of course, there's a problem of this random advice string, right? Because we don't have time to generate this random advice string. It's a random advice string of m bits. And we want to do things in square root mn, which can be much smaller than m. So we cannot write down this string. We can also not assume that it's given, because why would it be given, right? So we have to be a bit smarter. Classically, what the trick is what people call lazy sampling. That just means that you can assume access to an arbitrarily long random advice string by just whenever you query for a bit, you just generate it. Like you just, so it's lazy in that sense that it's not really there, but just you can assume that it's there and that it's fixed. But whenever you query it, that's when you basically generate a random bit, and nothing changes. You can generate bits on demand. But quantumly, this is not possible, right? Because we can address, in some sense, all bits at the same time in superposition, right? We can do queries in superposition, and so we need some kind of object there that we can ask for, to which we can perform these queries. Okay, so this is kind of a very interesting distinction between classical algorithms and quantum algorithms, and we found a way to go around this. It's in 2 stages, right? So it's called the getting rid of random advice. Stage 1, here we work with the notion of a k-wise independent string. What does that mean? So we again look at a string of m bits, but we don't ask that it's uniformly random. We only ask that it's uniformly random on subsets of k bits. So that means for every subset of k bits, if you take the expectation or you look at probabilities, then this behaves like a uniformly random string. But if you can look at larger sets, this is not the case. So it's kind of a non-trivial notion, but it's a significantly weaker object than a uniformly random string. Okay. So why are we interested in this thing? Okay, so probably should have showed this. So it shows that for every subset S of size at most k, we get that the bits in the subset behave like a uniformly random string, pretty much. Why are we interested in this? We're interested in this because one can show the following thing, which is kind of a folklore fact in quantum algorithms, that quantum algorithms cannot distinguish uniformly random strings from two Q-wise independent strings, using at most Q queries. So that means, you can imagine that you have a quantum algorithm that has query access to a very long string, and you're asserting that it's uniformly random, and I want to falsify this, then I need a lot of queries, basically. And this is kind of intuitive, but you can formalize this. You need a lot of queries to distinguish whether it's only two Qis independent or whether it's fully uniformly random. This you can prove pretty straightforwardly using the polynomial method, which I'll skip for the moment, but it's quite easy to prove this. But that's good because now we know that if I have a quantum algorithm which takes like t steps, so also makes most t queries, only requires two T-wise independent advice instead of uniformly random independent advice. So we're already kind of making the game a bit easier because we're no longer asking for a uniformly random string. We're asking for this weaker object, which is only two T-wise independent. But then, of course, we're again stuck with the same question, like how can we now assume access or simulate this weaker form of advice? Because again, like this string still has m bits, and so we still cannot write it down. A classic construction for constructing, let's say, two T-wise independent strings or simulating query access to two T-wise independent string is by looking at random degree 2T polynomials. So you can show that for any subset of 2T indices, the evaluation of this random polynomial will behave uniformly random. But of course, evaluating such a polynomial, again, takes a lot of time, too much time for us per query. So again, we looked a bit better, and we got lucky once more. Namely, there is other interest in this kind of object. It's what it goes by the name efficient k-independent hash functions, which is basically just the question of can we assume query access to a k-wise independent random string without completely generating it beforehand. And then again, there's very recent work by Cristiani, Paga, and Torup, and it's nice because before this work, we wouldn't know how to basically solve this problem. But because of this work, which is recent, namely is from 2015, we actually do know how to solve it. What they show is that you can basically, in O tilde k pre-processing time, construct a data structure that allows you to query a k-wise independent string in time O tilde 1 per query. So you do some pre-processing time, which scales as k, which you can expect, right? That's kind of the randomness that's needed. But then, once you have this data structure, you can just simulate queries to this much larger object, which is not really there, but you can simulate queries to it, and only O tilde 1 time per query. So we're very thankful to them. And this gives us the following corollary, which says that any time t quantum algorithm that uses uniformly random advice can actually be simulated in time O tilde t without advice. So that's nice because that allowed us throughout our work to always assume that we have this random advice string. And then afterwards, we just simulate this string and get rid of it. So now that this brings us to this updated quantum iterative sparsification algorithm, so as a kind of, to kind of summarize, we use a quantum algorithm to construct these disjoint spanners, right, that identify the important edges. Then we construct this k-independent oracle, which will allow us to simulate queries to a k-wise independent string. And then we use this oracle to kind of mark which edges are still there and which are no longer there. And this simulates a uniformly random advice string, and so we know that that works. Per iteration, this has a complexity square root mn over epsilon squared, which is basically dominated by this first step, right? We have cost square root mn to construct a spanner, and we have to construct 1 over epsilon squared of them. So this becomes our cost, and this becomes our algorithm in total, right? So this was just the cost of 1 iteration, but now we want to do it for a lot of iterations. So you start from this graph to which you have adjacency list access, you construct these spanners, and this k-independent oracle, and you can basically iterate it a couple of times, and in the end you get an implicit description of the final graph, and the final edges which are still present are kind of implicitly marked. And then you can just use Grover search to explicitly find the remaining edges, which is now just n over epsilon squared edges, and so that you can find in definitely in this time, like even less time.
Excuse me. Can you remind us what the value of k is there? I've lost it somewhere.
K. Oh, k would be. So you kind of describe your full algorithm, assuming random advice. You look at the runtime of the full algorithm. That would be k. Yeah, so assuming access to uniform random advice string, the runtime would be square root mn over epsilon squared times the number of iterations, but this is just logarithmic. And then in retrospect, you kind of replace this uniformly random string with a random string which is just square root mn over epsilon squared independent. Yeah, and so the preprocessing time basically scales with the runtime of the algorithm. So that's why you can always do it for free. So this gives us the following algorithm. We find a epsilon spectral sparsifier with n over epsilon squared edges and times square root mn over epsilon squared, which is not quite what I promised. So there's a second hack that we can do, which is basically constructing a rough spectral sparsifier and then using that to like approximate better sampling probabilities for the original graph. It's kind of surprising that it's possible, but this is a technique that has been used before. And so basically, there's some details, but you can basically improve the epsilon dependency to linear. So you get an Otilla square root mn over epsilon algorithm. That was our quantum algorithm. We proved a matching square root mn over epsilon lower bound. So I'm going to go a bit, say a bit high level here in the interest of time. The intuition of the lower bound, which is not doing ourselves very much honor because the intuition is very simple. The intuition of the lower bound is if you want to find n marked elements among m elements, then this takes square root mn time. Basically, it takes square root mn queries. So, definitely that much time. What we're doing is basically finding among m edges n over epsilon squared edges, which are special, which constitute the sparsifier. And so using this lower bound just gives you square root mn over epsilon lower bound. So that's the intuition behind the lower bound, right? We have m edges and we want to find this sparsifier which has n over epsilon squared edges. But of course, so there's a lot of details in how to, concretely formalize this. So what we did is we looked at certain random graphs of the following form. They're just bipartite, and you just connect every left node to like half of the right set of nodes. With 1 over epsilon squared nodes here, 1 over epsilon squared nodes here, and so that you would have 1 over 2 epsilon squared, epsilon to the power 4 edges. Then you take a bunch of these, and why we're interested in this is that you get a graph which has n over epsilon squared edges by basically taking n copies of that, or like epsilon squared n copies. And you can prove that, and so this is a technique that they use in the classical case, that this graph cannot be further sparsified to some extent. So any sparsifier of this graph must contain a constant fraction of the edge of the original graph. This does not contradict the fact that you can always find sparsifiers because this graph is already sparse. It already has n over epsilon squared edges, and you cannot further bring this down. That's what they prove. So that's interesting because now we know how to construct a sparsifier. We can construct a graph which is already a sparsifier and cannot be further sparsified. And now the idea is you construct a sparsifier, so this is a graph which cannot be further sparsified, but you hide it in a larger graph. So you basically add a lot of nodes and edges, and you kind of hide these different copies. What you do is you set a weight to these edges of 0, and these have a non-zero weight, and then you can prove that any sparsifier epsilon spectrum of this large graph must identify all these smaller subgraphs. And that's kind of the idea. Again, there's like a lot of details in how to like really implement this and do this in a kind of black box way. But yeah, that's what we did. At some point, we reduced the problem to a quantum lower bound for the composition of a OR function with a relational problem. And a relational problem is basically what we're working with, right? A relational problem is a problem where a valid output is not necessarily unique. If you want to sparsify a graph, there might be a lot of sparsifiers, and any of these would be fine. So you get a sort of generalized problem, which is a relational problem. But the composition of quantum lower bounds for relational problems was not clear, so we asked some world experts what their opinion was on this, which I thought Ronald was, but then he said like there's even better experts, which turned out to be Alexander Belovs and Troy Lee, and they actually independently sent us a proof of this thing. So basically you can, if you have a relational problem which has lower bound L and you compose it with the OR over n bit functions, you can kind of, what you would expect, you find a lower bound which is L times square root n. But I mean, clearly proving this is kind of non-trivial, and this is a paper that they'll publish basically in some weeks, I guess. So in our case, L would be n, capital N would be m over n epsilon squared, and so we find that the query complexity of outputting epsilon spectral sparsifier of a graph takes O tilde square root mn over epsilon time. So this is a matching lower bound for our algorithm. All right, and I'll quickly just go over why we're actually interested in doing all this stuff, which is finding quantum speedups for problems which are, at least we believe are more relevant. One example would be min-cut, right? So you're given a graph, and you know that to every subset S you can associate a cut value. Now you want to find the minimum cut value. So basically what you want to do is you want to cut the graph in two. Like, how do you optimally do that? So you want to find the kind of cut with the least number of edges, or at least the least number of weights. This problem is called min-cut. Classically, you can find the exact min-cut in O tilde m time. This is already long known. This was an algorithm by Karger. What we can do now is, it's also something that they already classically do, and I already mentioned this before, is that you can first sparsify the graph and then solve min-cut for the sparser graph. So clearly the downside is that you'll only get an epsilon approximate solution, but okay, let's just be happy with that. So what we do is we sparsify the graph and we solve min-cut on the sparser instance. But what's interesting now is that the sparser instance will only have n over epsilon squared edges. And classically, we can solve min-cut on a graph with n over epsilon squared edges in time n over epsilon squared, pretty much. And so the main cost will be the sparsification step, which we now know how to do more efficiently, right? We can do this in square root mn over epsilon, and this will be the dominant factor. So we find the O tilde of square root mn over epsilon algorithm for epsilon min-cut. And you can kind of do the same trick for all these algorithms and find speedups for max cut, min-cut, min-st cut, sparsest cut, and so on. Similarly, you can think about solving linear systems. So general linear system of the form Ax equals b, given A and b, you want to find x. Here the complexity is O tilde min m times n, or n to the power omega, where omega is the matrix multiplication coefficient. For Laplacian systems, you can do better, which is basically what Spielmann and Tang proved. For a Laplacian system, you can solve the problem in O tilde m, right? Which brings it down to O tilde n squared. We can do the same thing, pretty much. What we can do is we can prove that, basically the fact that I mentioned earlier, you can solve the Laplacian system in the sparsifier and approximate the original Laplacian system. So again, what we do is we apply quantum sparsification on this original graph, which takes square root mn over epsilon time, and then we just apply a Laplacian solver on the sparsified graph, which is now going to be a very small cost. So the cost again dominated by this first thing, and so we get a square root mn over epsilon quantum algorithm for Laplacian solving. So Laplacian solving is kind of a nice gateway to again a lot of other things. So we find this epsilon Laplacian solving improvement that gives an improvement on estimating effective resistances, cover times, eigenvalues. You can do things like spectral clustering and so on, and you'll find a very similar speedup for all of these problems. And so to end this talk, I'll just mention some open questions, which are still, well, I mean, not all of them are still open, actually. So one open question is we have this quantum Laplacian solver which has complexity square root mn over epsilon, right? Basically, we construct the sparsifier, now we solve the system. But classically, there are smarter ways to work with sparsifiers that get rid of this epsilon dependency. So they can basically solve Laplacian systems in U tilde m log 1 over epsilon. So the question is, can we do the same thing quantumly? Can we improve this epsilon dependency to log 1 over epsilon? And so we were actually strongly convinced that this should be possible, but as it turns out, thinking a little longer shows that it's not possible. It's kind of interesting. You can prove that you need a polynomial dependency on epsilon, basically, for quantum Laplacian solving. So that's kind of differentiates the classical case from the quantum case. Second question is, Laplacian solvers led to breakthrough algorithms for problems such as max flow in very non-trivial ways, for using very nice techniques. So we can look for quantum speedups for the same sort of problem. Max flow, rate problem is matching. So these are problems which are still, so there's some quantum algorithms for them, but they use like the old school techniques, like the combinatorial techniques. Like now these new algorithms, they use these linear algebraic techniques, and so nobody thought about what we can basically find using these techniques. Then there's the thing that I mentioned before, like exact min-cut can classically be solved in U tilde m time, right? Using Karger's algorithm, we only find an epsilon approximate min-cut in square root mn over epsilon. So we can ask the same question, can we also find the exact min-cut? Because surprisingly, this classical algorithm also uses sparsifiers. So you think like as soon as you use sparsifiers, you kind of you get this epsilon error and you can't get rid of it anymore. And so it turned out that you can. So we thought like, okay, maybe we can do the same thing quantumly. Again, it turns out you cannot. So maybe I should update the slides. It seems basically it's the same thing. You can kind of show that min-cut quantumly, exact min-cut cannot be done faster than U tilde m. The idea really comes down to if I give you if I give you query access to, let's say, the graph, and you want to estimate the sum of the weights, say something like that, then you cannot get, if you want to exactly do this, if you want to find the exact sum of the weights, then you need m queries basically. Let's say you want to find an epsilon approximation of the sum of the weights, then you can do it sublinearly, but you get a polynomial epsilon dependency. You cannot do it in sublinear time times log 1 over epsilon, something like that. And it turns out that min-cut in some sense can be reduced to this problem. And so we show that actually if you want to find the exact min-cut, we think this is kind of interesting, you cannot beat classical algorithms. And then finally, spectral sparsification has been extended to more general objects like hypergraphs, sums of PSD matrices, streaming setting, and it's related to very nice field of research like spectral sketching and data regression. Can we similarly find a quantum speedup for these problems? Okay, so that was my talk. Thank you very much for listening.
So there, if you compare, I mean, this is always going to be slower, right?
Wait, but so we assume sparse access, right? Because like if you want to have a dependency which is like not n squared, like I mean, adjacency is like sparse access basically.
Yeah, so you will get in that case, in the Walsh case, you will get like, okay, if you have a square root kappa dependence, then it will be like n.
So you're thinking about HHL type solvers. Okay, so HHL type solver, I think what these techniques are mainly interesting for graphs which are denser. So HHL is very interesting for graphs which are very sparse, but I mean very sparse in the sense that like sparse is basically a constant, something like that, maybe some log factor, and the condition number is good.
So you'll get something like, so if you do algorithms for sparse graphs, you'll get something like n to the 3 half or something. So in this case,
you would even get worse, you n to the power 3 actually, because kappa can be as bad as so the spectral gap can be as bad as 1 over n to the power 3. And this would be for non-sparse graphs even, so. Yeah, so it's really, I mean, like for graphs that are well conditioned and are very sparse, like, you know, constant sparsity, something like that, then HHL is very interesting. But for most other graphs, it seems like.
And all these results, they hold for both weighted and unweighted graphs. Like the results.
Yeah, even more so, yeah, but I mean, of course, you know that I think that for unweighted graphs, you can actually do better than that. Like all our lower bounds, they all rely on the fact that you have weights. And even like, we use like polynomially large weights sometimes and so on, and that allows you to, gives you a lot of freedom. Like it's kind of related to this problem, like I said, that if you want to estimate the sum of the weights, then this is hard. But if the graph is unweighted, you just got to know what the number of edges is, and this you can do pretty easily.
I maybe have a naive question. But this unspecified graph that you showed, you said that you can use this unspecified graph to put them in a larger graph, and the algorithm is sufficient to identify it. So can we characterize this unspecified graphs? Because it looks like they need to have a certain extent, to have a certain number of nodes, because if not, it becomes too simple and you can get rid of them in some cases. So
wait, can you say it again? I'm not sure.
So for example, like you just have 2 nodes and an edge. This cannot be a specified graph, because in a large graph you will cut some.
Well, I mean,
edges, so this cannot be described as an unspecified graph.
it can be an important, like basically there's edges which are important, and that you know should be present in the final graph. By Spielmann and Tang's work, you kind of know that a graph can have pretty much n over epsilon squared important edges. But it's not clearly how to characterize these. Like, you know that you need at least n over epsilon squared edges to like characterize the graph. And so what we did here is like we worked the other way around. We started from kind of planting, you know, important edges, and then adding a lot of edges which are not important.
Yes.
And then we know that you need to find these ones.
Okay.
So the current results for like finding max flow uses these Dirichlet algorithms?
No, for max flow, I mean, this is Ambeniz and Spalek, and they use like Goldberg-Rao stuff, I think. So this is like, it's really nice to, you know, look into all this stuff. Like there was all these like older combinatorial algorithms, like the time of Robert Tarian and so on, these guys, and so they were all about like finding exact solutions to combinatorial problems, like finding an exact max flow and so on. And then they use these combinatorial algorithms like, you know, push relabel algorithms and so on. And these worked nicely. I mean, they worked exactly, but like they had a runtime which, like, I think this max flow algorithm by Goldberg-Rao, I think it has some like m times n to the 1/3 depends, something like that. So they always get an overhead with respect to like the optimal, you know, runtime. And so this quantum algorithm by Ambeniz and Spalek uses this work. But then there's later work which is, you know, followed from a lot of these things, which brings everything down to O tilde m pretty much. And so now, you know, the game is open again to, you know, find a better max flow algorithm.
So there are no more questions. Let's thanks everyone again.
Thank you.